All right, we're going to look at the 4-2 notes in transition to college math. Number bases and positional systems. So we're going to change numerals in bases other than 10 to base 10. So that's the first thing we're going to do. I would like you to copy some of these down. We will later need to know like that 5 to the first is 25, 5 squared is, or 5 to the first is 5. 5 squared is 25, 125, and 625. And then 4, 16, 64, 256. So the first thing to get in our notes is that when a numeral appears without a subscript, it is assumed that the base is 10. When you see the number 73, written like 73, you can assume it represents 73 things the way we're used to seeing it. Bases other than 10 are indicated with a spelled out subscript. So 1, 2, 2, 5. So that means 1, 2, 2, base 5, and we'll talk about what that means. In base 5, you'll never write the digit 5, because once you get to 5 things, you start over as 1, 5, and 0 ones left over. Similar to when we write the number 10, we go from 9 ones to 10 ones, and then we start counting again. So let's take a look at what this looks like. These numbers represent places, and it's a 1's place, a 5's place, a 5 squared's place, and a 5 cubes place. So that's how we evaluate this number. We have 2 1's. We have 4 5's. We have 1 5 squared. And we have 3 5 cubes. So the number 3, 1, 4, 2, and base 5 represents, as far as we're used to seeing it as, the number, so 2 1's, 4 5's, 125, and 3 125's represents the number 422, as far as we're used to seeing it. Let's see what it looks like with the 8's. 6 1's, 2 8's, 7 8 squareds, and 4 8 cubes. And we add those up. Transition kids typically find this pretty easy. This kind of makes sense. So 4 7 2 6 base 8 would represent 2 5 1 8 in our base 10. So let's kind of summarize the work we just did, changing to base 10. To change a numeral into a base other than 10 to a base 10 numeral, find the place value for each digit in the numeral, multiply each digit by the numeral in the numeral by its respective place value, and find the sum of the products in step 2. So let's take a look at what that looks like. If I do have 1 2 2 in base 3, I'll have, so the place value for each digit in the numeral, 2 1's, 2 3's, 1 3 squared. Multiply each digit by the numeral, 2 times 1, 2 times 3, 1 times 9. Find the sum, add them up. 9 plus 6 plus 2 should be 17. And that is our base 10 numeral. So let's try it again. 1 1, 3 6's, 4 6 squareds, 5 6 cubes. Add them up. 1080, 144, 18, 1, add them up. 1243 would be our base 10 numeral. 2s are the ones that always look a lot bigger, but they actually represent pretty small numbers. The only numbers you're going to see in 2 are 1s and 0s, because when you get to 2, you count over. So I have 1, 1, 0, 2s. Where'd that 1, 1 go? 1, 2 squared, 0, 2 cubed, 0, 2 to the 4th, 1, 2 to the 5th. We add those up. 1, 4, 32. We actually only get the number 37. All right. Something else to get in our notes is that when we have bases higher than 10, we can actually write them like even base 16, letters we start representing as numbers. So I would copy this chart into my notes, and then let's try an example. 7 is still 7, and its 1's always first. C from my chart represents 12, and our base is 16. And E from our chart represents 14, and it's 16 squared. So we add those up.